Hello static students. I want to begin our discussion in section 2.1 through 2.4 of Hibbler, and we're going to talk about scalars versus vectors. You may remember from prior work that a scalar has magnitude only, and some examples might be length or mass or time. However, a vector has magnitude and direction, and a map might be a good way of getting started with our understanding of vectors. Let's say we have a point here in Meridian. This is a map of the Boise area, and let's say we want to go about 5 miles north, and we'll get to Star. And let's say we want to go another 5 miles, and let's go over here 5 miles east, and we get to Eagle. Where did we actually go? Well, we actually went from where our beginning position was to where we ended. So that's our actual, and we may call that our resultant. It is made up of those two legs or constituents, and we'll call those components. Now you may understand also that that's not the only way to get from wherever our beginning position was to our end, and we can perhaps go all the way to Boise and then take State Street all the way back, and we could have got there by a variety of methods. And so that's kind of the takeaway here, is that there are many ways, multiple ways of getting from point A to B, and we're going to talk about how we're going to add those components together to get a single predicted resultant. Well, let's add some vectors together, and let's say we have a vector going in this direction. We'll call that P, and another vector in that direction, we'll call that Q. And when we add them together like that, we'll still get a resultant. We call this the triangle method, and when we add them tail to head or head to tail. And you can envision that these components are arrows, where that's the arrowhead, and this would be the tail, or the tail of that one. When you add them together tail to head like that, you form a nice little triangle, and we call that the triangle method. Clearly that's not the only way of getting from this point to this point, and so we could add two other vectors. We'll call that P prime and Q prime, but we still get the same resultant. So again, we'll form a triangle, and that's still called the triangle method, and there's obviously multiple ways of getting to R. Now, a couple things I'd like to point out here with forces. We're going to be dealing mostly with forces in this course. Forces have magnitude and direction, and basically at this point we're going to say that there's no difference between pulling and pushing. For example, if you have a box here and you're pushing here with a force P, and if the force kind of is going in this direction, there's no effect. There's no difference in the effect of whether you're pushing or whether you're pulling in that direction. Same thing happens here if you have this bracket. If you have this force of 40 pounds pulling in that direction, there's no difference in effect in how we look at that. You could have a force pushing here, 40 pounds, or you could have it pulling with 40 pounds, and it's the same thing. So the point here is, don't be too confused whether it's a pulling force or a pushing force. You add them together in exactly the same way. We'll talk about what some of these things mean as we go along. But when we add the vectors together, we will add them in the same manner, regardless of whether it's a pushing force or a pulling force. Well, when we have vectors, as we've talked, where if you have a component going in this direction or a component going in that direction, in the triangle method, we can also add them. This is called, again, the tail to head method. Where those are the tail and the head. You can also add them tail to tail, and we find that with force vectors this is often pretty convenient. So in other words, we can add them just like that, where the two tails are added together or positioned together, and then when you do that, you draw a little parallelogram, really, where you draw a parallel line from one force. Where this is one force, you draw a parallel line, and where this is another force, you draw another parallel line, and where the two parallel lines intersect, that's where the resultant would be, or the position of the resultant, and that's really handy when we're doing force vector addition. So again, what this is called then, this is called the parallelogram method if you're adding forces tail to tail. And again, that's obviously not the only way to get there. You could have had a force going down this way or a component going that way. Obviously you get there with the triangle method that way. Or you can do that with the parallelogram method. You can say I want to have a component this way and a component this way, where this force is going to be the same as that force, and then when you add them together using the parallelogram method, you just draw parallel lines parallel to the two forces, and you still get the same resultant. The same resultant would happen in either way. So again, this is called the triangle method if you do it this way, tail to head, or the parallelogram method if you add them tail to tail. We are going to be dealing a lot with parallel lines and with triangle lines, or with triangles in this course. So just a little bit of review of trigonometry that we might want to deal with right now. But let's say we have this set of parallel lines that is given right here, and if we cut it or draw another line intersecting that, we can see that there are some angles that are formed. And I'll call this angle alpha, and that's going to be the same as that angle alpha. And it's going to be the same as this one, angle alpha. In other words, the angle between those lines is going to be similar because of the relationships. We may also find that if we draw another set, or another line that is going to be parallel to the first line, we'll have the same angle right there. And then we'll have that angle inside there could be the same angle alpha. In other words, if you have sets of parallel lines that are intersecting, form some similar angles. If you now draw a line between those two intersecting points like this, we now have a set of similar triangles. In other words, this angle or this triangle is going to be similar to this triangle. And we know similar, what similar means is that the angles and the sides will be related. In other words, this may be side A will be the same as that side A. And if this is side B, that'll be the same as that side B. They'll have a common side, which will be called C. And we can see that those angles then are going to be similar on the inside. This will be the same angle here as the same angle there. Okay? And we also remember that for any triangle, for any rectangle, there's going to be 360 degrees. Any rectangle, parallelogram, actually any four-sided figure, there's going to be 360 degrees of, if you add all the inside angles like this, all those angles will be add up to 360 degrees. All right. Now for triangles, this is a common way of describing a triangle, but for any triangle, we're going to say that there are going to be internal angles, A, B, and C, and there are going to be sides that are going to be opposite of those angles, capital A, B, and C. Now, we're not always going to be using those letters or those kinds of descriptions, but for right now, let's just suggest that side A is going to be opposite little angle A, side B is going to be opposite B, and C is going to be opposite C. And there will be 180 degrees when you add all those together. That's just something that we know, and we can obviously say that, but we can say A plus B plus C is going to be equal to 180 degrees, and that will apply. Okay, another thing that happens on any triangle is that the sine law applies, and we may write that if you haven't written that for a while, but just go ahead. We're just going to say the sine of angle A over side A is equal to the sine of B over side B equal to the sine of angle C over side C. The cosine law also applies. And the cosine law, if you recall, it says that c squared is equal to a squared plus b squared minus 2ab cosine of angle C. Now again, just to recall, or just to notice that the side C is opposite the angle C. In other words, the side C is opposite the little angle C, and then this would apply. Now for right triangles, we have a special case that happens, and the same cosine law applies, and I've just duplicated that right here. And so the cosine law applies for any triangle. Obviously it applies for a right triangle too, but just notice here that side C is going to be opposite angle C, and if C is going to be a 90-degree angle, if this is a right triangle, C is going to be equal to a 90-degree angle, the cosine of C, or cosine of 90 degrees, is actually equal to 0. And so this whole term goes away, and what you're left with is the Pythagorean theorem. And so the Pythagorean theorem is then a special case of the cosine law. And other things that just to remember is that all of the sine, cosine, tangent, standard relationships that apply to right triangles. And here we just notice that the side C is the hypotenuse of a right triangle. So that if this is angle theta, this is going to be the side opposite, side adjacent, and the side and that'll be the hypotenuse, and then the sine cosine relationships apply. So again, hope that you're familiar with that, and then we can use those going forward. Well, we're going to use these new skills now to solve a little problem. We're going to try to find the resultant of these two forces. And you can see that there's an 800 Newton force going up, a 600 Newton force going in this direction. And we're going to use the parallelogram method to try to solve this. So the first thing we want to do is draw the forces, perhaps redraw the forces in the magnitude, or make those arrows about the same length relative to each other as the magnitude of the forces relative to each other. For example, we can see that they're drawn about the same length, but the 800 is obviously bigger than the 600, so I'm going to redraw this force so that it is up going this way, so that this now is the magnitude of my 800 Newton force drawn like that. And then we're going to draw parallel lines from those forces and find out where they intersect to find out where the resultant would be. So let's go ahead and draw those parallel lines. And then when we do that, we can see that the resultant goes right there. That will be the resultant. Okay, we don't know the direction and we don't know the magnitude of the resultant. So let's define our direction. I'll call that angle phi. And the resultant magnitude will become obvious here in a little bit. Now, how do we do that? Let's look for some things that we might understand here regarding some of the angles. If this is angle 30 right here, then, and this becomes a right triangle here, the reason that's a right triangle is because that force is going straight up. This looks like that's going to be 60 degrees. And if that is 60 degrees, because this is now a parallelogram, we can say that this angle up here is also 60 degrees. That's about all we can find so far. Now we're going to redraw this triangle here. We can see that there's a triangle that's formed right here. And let's redraw that over here on the side, and let's use the triangle method to do some of the analysis that we might need. So here's my resultant. I have a 600 Newton force going down this way, and an 800 Newton force going up this way. I have an angle here of phi plus 30. And we also know that this is angle 60 down there. This is the resultant. Now let's use the cosine law to try to find the magnitude of this resultant. Here again, this will be the thing we're looking for. We have an angle that's opposite that side. So the cosine law is a good and easy way of doing this. So I'll just say that r squared is equal to 600 squared plus 800 squared minus 2, 600, 800, cosine of 60. Now the only unknown in this whole thing is the resultant, and so you just do a little arithmetic here, and you can find that the resultant here is going to be equal to 721.1 newtons. And there's the first thing that we were looking for. We're looking for the magnitude of the resultant. The direction. Actually, what we're looking for in the direction is this angle phi. So how do we, and that's also part of that component there. How do we get there? Well, maybe the sine law might be an appropriate way. So let me just scooch this up here a little bit. And let's use the sine law to see if we can find out what angle phi is. So this is the cosine law. And now let's use the sine law. All right, And so in this case, what I'm going to do is I'm going to say that the sine of 800 here is going to be opposite this angle. And now that I have this resultant, I'm going to say that that's opposite that angle. So let's just do the sine of 800. 800 over the sine of phi plus 30 is going to be equal to r, which is our new value, over the sine of 60 degrees. Plugging this value into here, well, I'll go ahead and just do all the arithmetic for you. Let's just do that. I'll just say that sine of phi plus 30 is going to be equal to 800 over 721.1 sine of 60. Evaluating that, then I'm going to say that phi plus 30 is equal to the inverse sine of 800 over 721.1 sine 60. Taking the inverse sine of that, and then you can find that's equal to adding those two. When you take the inverse sine of all that, you'll see that this is equal to 73.9 degrees. Then evaluating phi, you get that as equal to 43.9 degrees. So again, there's a good way of doing the sine law and the cosine law to find out what we needed about this little problem. Okay, well, that should help you out to get started on some of these trigonometry problems, and we'll move on to the next section.